Hi, everyone. Thanks for coming today. My name is Emily. I'm a software engineer at Benchling. And today I will be talking about a GraphQL API we built at Benchling last year. It was dynamically generated and included custom types at runtime. So a quick overview of the agenda and what I'll be speaking about today. First, I'll talk through the Benchling use case. Then I'll give a brief overview of existing GraphQL APIs that we looked at as part of this project. Then I'll talk about what we did to dynamically generate a graph at runtime, walk through some of the technical challenges, and then leave some time at the end for Q&A. So to kick us off, I'm going to talk about the Benchling use case. So what is Benchling? Benchling is a biology-first platform for scientific data, collaboration, and insights. So here are just a couple screenshots of the Benchling application. It's specifically designed to help scientists do their jobs more efficiently. And so if we zoom into one of the applications here that we offer at Benchling, here we're looking at the biomolecule design application. And for the purposes of this talk, what you'll need to know is that this application helps scientists design their DNA sequences, their RNA sequences, and those are the sorts of data and data models that we're going to be persisting in the database and care about here. So looking a little bit closer into that example Benchling application. So this biomolecule design application we were just looking at, you might imagine in the database we have a corresponding sequence database table representing the sequences in our application. And the sequence, for the purposes of this talk, let's say it has two properties. It's going to have an ID, and it's also going to have bases, so like AA, TC, G, representing the bases of your DNA sequence. And if we were to translate that database table type into a GraphQL SDL type, you might represent it something like this, where you have your Benchling sequence type, and it has IDs, and it has bases. Now, something that's really unique about the Benchling application is that we actually allow our customers to define their own types. So we start with this built-in, out-of-the-box Benchling DNA sequence type. And customers can actually come in and create their own custom DNA sequences to help model their data and their experiments. So what this actually looks like in Benchling is that we have this UI. You go in, you can name your custom type. So maybe in this case, we're going to call it a plasmid. You can specify which of the built-in types you're going to extend. So in this case, the DNA sequence. And you give your type some new properties, right? So in this case, we're saying that we're going to make a custom plasmid type with a weight property, and that's going to be a decimal. And all of this information is then persisted into the database for that particular customer. And so once you have a custom type, you can actually record data against that custom type. So this is like an instance of a plasmid, which we have just saw was a custom DNA sequence. And so on this plasmid instance, we have our custom fields down here defined by the customer. And then we also have all of these built-in fields that come out of the box with the Benchling application. And so finally, why build a GraphQL API? So now we've talked about, at Benchling, we have these built-in types. We have these custom types. What do we need a GraphQL API for? As you might imagine, customers of Benchling really want to be able to get their data out of Benchling in an easy and intuitive manner. And so in order to build a UI like this, where you're able to search for all the types that you might have in your Benchling database, click on some fields of those types, and then get that data out of Benchling, GraphQL is really well, serves this use case really well. So that dropdown, you can imagine that's coming from an introspection query in our graph, and then all these fields are going to be coming from our graph as well. So how are we actually sort of representing these types in our GraphQL SDL? So if you look on the left-hand side here, this is how we have decided to represent those built-in types that come out of the box, right? So we have a sequence interface that's going to represent those shared properties that come from the built-in types. You have your Benchling sequence, which is that built-in type implementing that sequence interface. And so then for any customer-defined types that are also implementing that sequence interface, we'll go ahead and tack on the additional properties that the customer has defined. So in this case, the weight. And so from custom types, we now have the concept of custom graphs. So you can imagine we have customer A here. They've defined their own custom sequence. Their graph is going to look very different from customer B. Maybe they have their own sequence that they've defined with additional properties. So we have two different graphs that we're going to have to serve here for these two different customers. Another property of these graphs that we're dealing with is that a type in the graph can change at any point in time. So if we remember that module we were looking at before, we were kind of going in, creating your type, defining those fields for your type. The customer can do that at any point in time. So they can go in, add a type, delete a type, change the type of a property, and that's going to change their underlying GraphQL graph. Another property that I think is pretty unique to the Benchling data model is that all of our graphs for our customers are highly connected. And what I mean by this is that if we take that custom plasma type we were looking at before, you can imagine that it is connected to many, many other types in the graph. Right? A customer can define a custom type that is connected to another custom type, which is then connected to a third type. And each of these types could also be connected to things like results and the folder that the data is in. And these are all nodes in our graph. So the graph ends up being extremely connected. And then finally, talking a little bit about the scale we're dealing with here, right? So at Benchling, we have over 100 built-in types that are going to come out of the box. So that's going to be that Benchling DNA sequence type we were looking at before. And then some of our customers end up defining thousands and thousands of their own types. So some of our customers have over 5,000 types that they've defined and over 40,000 enum members. So we're talking about the scale of the graph we're building here. It's a lot of types in the graph. And so finally, that leads me to the fundamental problem we're trying to solve at Benchling, which is that we needed to dynamically generate a graph per customer at runtime at scale. And so that dynamic generation is coming from the fact that each customer's graph looks different, and they can change the types in their graph at any point in time. And then that scale portion is that there's really no limit to how many types a customer can make in Benchling. And so some of our customers really have taken that to heart and made thousands and thousands of custom types in their Benchling application. So when we came to tackle this problem, the first thing we did was look at existing GraphQL APIs and see sort of what's out there today. And so here I'm just showing two commonly known public GraphQL APIs. We have the GitHub GraphQL API. We have the Shopify GraphQL API. And so in these GraphQL APIs, typically the types in the API are generally well known, right? So we have for GitHub, maybe a viewer, an organization. For Shopify, you might be looking at shops and products. And something to note here is that typically they contain on the order of hundreds of types in the schema, not the tens of thousands that we're looking at Benchling. Furthermore, most of these APIs actually have just statically defined schemas. So if we zoom into the GitHub API here, you can actually go online and download the schema that they're using to generate their API directly. And so this is a static document. All your types are sort of known. And this is different than what we're building, which is having to include all these custom types at runtime. And then switching over to looking at GraphQL frameworks. So once we sort of surveyed the landscape of public GraphQL APIs, then we thought, OK, how are we going to go and build our GraphQL API? So when looking at frameworks we might use, the two main ones we were considering were Ariadne and Strawberry, which, as you might know, one is a spec-based framework, one is a data class-based framework. But what is sort of key about this is that most or all existing frameworks we evaluated expect your schema and your types to be statically defined, right? They sort of just expect that you have a file that lists out all your types, and there's not really great support for that dynamic generation that we need. And so we ended up going with Strawberry for a couple of reasons. It had some features we needed out of the box. And so I'm just going to talk through a little bit about how Strawberry works. And so for Strawberry, what you do is you define your types as data classes annotated with strawberry.type. Then you define your data set, which is a function that's going to return objects of your type. You define your resolver, and you attach it to a field on your query type. And then finally, you can generate the query and the schema from there. Great. So moving on, how did we generate these dynamic graphs, right? We were talking through some possible solutions, sort of seeing that they support static graphs really well. And so we're kind of needing to bend the framework a little bit to get this dynamic graph generation working. So the first step here is that we decided to do our type definition via GraphQL SDL as our language. Some reasons we chose this was that we wanted to promote spec-first development. GraphQL SDL also provides clear and declarative syntax for all your types. And it is generally pretty flexible and extensible. Like you could add a lot of different metadata into your SDL document. Some cons here is it can be pretty verbose, right? So if you want to implement an interface, you actually have to list out all the shared properties on every single type that implements it. You can't specify nullable but required values, which something that came up later down the line when we were looking at input types. And there also currently is no support for directives on enum members, but hopefully maybe that is soon to come. And so when we're thinking about defining our types in this SDL language, we have our built-in types defined actually statically in SDL, and then we have our custom types we're generating dynamically this SDL document for. And what we're doing is we're taking those two SDL documents and putting them together to create this combined SDL document. And so going forward, when I say combined SDL, this is what I'm referring to, the built-in types plus the custom types. And so once we have this definition of all our types, then we can go ahead and actually generate our strawberry data classes, right? So we're taking directly the properties on that SDL type and using that as our annotations for our data classes here. So all in all, this is the process we're going through. We're taking our built-in and custom types from the database, creating that GraphQL SDL document, and then generating our strawberry data classes in order to build our schema. One thing I'll call out about this process is the need to use forward refs when generating our types. When you look at maybe a statically generated schema, you actually have all your types sort of defined in the same file. So when you refer to another type, it's already defined, and you can go ahead and refer to it. However, in our particular use case, it might be the case that when you're generating that folder type, you haven't yet generated the user type. And so for us, what we did is on the first pass of generating our types, we'll replace all the references to other types with a forward ref. And then on the second pass, we'll replace all the forward refs with the actual types once we generated them. So that's sort of like something that we had to do in dynamic generation that you might not have to do when you're statically defining your graph. So next, after we've generated all of our types, now we have to generate our resolvers for those types. And so this is a pared-down version of what we ended up doing. Essentially, what we have here is a function that returns another function, which is a strawberry resolver function. It takes in the identifier for a given type and returns you back a resolver for that type. And finally, the last step is actually generating that schema on the fly. And so the process here is to loop over the graph of all of our types. We're going to be dynamically generating a list of fields. So for each type, we're appending a field to our query, attaching that resolver for the type, and then returning the schema for our query. So once we did all of that, in our GraphQL playground here, you can see now that we're able to query for those custom fields, right? So this is a custom type we were looking at before, that plasmid type. It has that custom field weight, and we're able to get the data for that custom field. Something I'll call out here is if you are on the journey of dynamic generation, you might not do exactly what we did. You might consider going directly to the data classes or directly to our Ariane spec. That would probably be a little bit more performant, a little bit faster. We decided to have that sort of middle SDL document step because we have other things at Benchling consuming that STL document. But perhaps if you were building just a GraphQL API out of the box, you might consider doing these two things. Cool. Great. So now I'm going to move on and talk a little bit about the technical challenges we faced during this project. So going back to that graphic of the graph scale that we're dealing with, right? This turns out to be one of our biggest challenges. Again, we have 100 built-in types. Some of our customers have over 5,000 total types and 40,000 enum members. So that's a pretty big graph. And this is a much greater scale than typical GraphQL APIs might expect. And so what ends up happening is that the introspection performance was pretty bad in the beginning. So it was over a minute in the worst case to actually be able to introspect the graph. And you can imagine as a customer trying to get data out of Benchling, that's way too long to be waiting to understand what types you might be able to query. And so if we dig into the performance breakdown a little bit more, we spend about 67% of the time constructing that combined STL document. So that's grabbing the built-in types, custom types, putting them together. And then we spend the rest of the time parsing the STL and constructing those Strawberry data classes. And so here are some mitigation strategies we considered for solving this problem. We thought about caching the type data directly from the database where we're storing it. We thought about caching that combined STL document I was talking about before. And then we also thought about caching the STL directly from the Strawberry graph, so caching that STL that you can generate from your Strawberry schema. We decided to do the last of these options. And the main reason being that there is really good front-end tooling for STL. And so you're kind of able to build this UI on the left-hand side here without even doing an introspection query. So if we're able to cache that introspection STL document, we can serve this UI, and we kind of bypass the need to perform an introspection query to begin with. And so this is an overview of our caching framework. The first thing we do is construct a hash key from the database dependencies. So this hash key is going to capture if a type changes in the database, if a customer changes the type of a property, if their permissions change, right? So maybe a user no longer has permissions to a particular type. We also have to remove that from their view of the graph. And so that hash key is going to contain all of that information. We combine that with the release ID. So we're actually making sure that the cache represents the most up-to-date version of our built-in types as well. And then all of that is used to create a path in S3 where we're actually caching that STL introspection document. And so if we look at our path and there is a document there, great, there's a cache hit. We're able to return it right away, dramatically reducing the time to serve there. And then, of course, if there's a cache miss, we are going to regenerate the graph, regenerate that document, and then populate the cache. On top of that, we also implemented a cache repair strategy. So this was to increase our odds of having a cache hit and essentially keep the cache warm to the best of our ability. So what we're doing here is that we have a sense of the active users, maybe for the past month, who have been actually using this API, querying for their types in Benchling. We keep their user IDs in a Redis cache different from the STL cache. And then every 30 minutes, we're running this async job to refresh their cache. So every 30 minutes, we look at the active users, we see if their graph is stale. And if it is stale, we'll regenerate their graph and cache their introspection STL document. And so after this caching effort, we're experiencing a 50% cache hit rate, which was pretty good. And it's dramatically brought down that introspection from over 60 seconds to less than a second in terms of just getting that STL document from the cache and serving it to the user. Cool. So now I'm talking a little bit about the performance per request. So we talked a little about introspection, how we're building that dropdown of types. We also, when serving requests, we do need to have the most recent version of the graph for data integrity purposes. And we can't really get around not building the graph because we do need those data classes to validate the response and return the objects. And so the main thing here is we want to avoid rebuilding the entire graph on every request, right? So remember before, it was taking over a minute to build a graph for some of our larger customers, and we want to avoid doing that as much as possible on each request. And so what we did here was come up with a subgraph strategy. And so what we noticed is that most queries that users are running do not include tens of thousands of types in the query, right? So if you look at this particular query, it's actually only touching 2 types in the graph. It's touching that plasmid type, and it's also touching the user type to get that creator ID. And so when doing a survey of all the queries that people were running, no more than about a dozen types, I would say, per query were actually being used. And so what we did here is that on a per request basis, instead of generating the whole entire graph, which was very, very non-performant, we actually just generate the subgraph of types for that particular query. So in this particular example, we're going to generate the plasmid type, we're going to generate the user type, but we can ignore all the other types associated with the plasmid. And this also brought down the time to serve by a lot. Before, we were looking at over 60 seconds to generate that whole graph. Again, this is bringing it down to less than a second to serve a particular request. So finally, just wanted to end with some acknowledgments. Lots and lots of people worked on this project over the course of a year, and just want to shout them out on this slide here. And yeah, I will now open it up to Q&A. Oh, yes. You want the mic? Here you go.
Okay,
nice.
there it goes. Thank you. When a user makes a change to the schema, say adding a new type, how quickly does it show up on the front end?
So in the UI, it'll show up pretty instantaneously. So you'll be able to create types of that schema right away. And then sort of for our GraphQL API purposes, it will trigger a regeneration of the graph.
Okay.
Yeah.
But that regeneration, that could take up to a minute because if you have to generate the whole thing.
Yep, exactly. So that would fall in sort of the cache miss category. So for 50% of the cases, we are still taking up a really long time.
Okay. For caching, I guess this is a follow-up question, but did you cache the entire schema, or did you break the schema into chunks so that each chunk could be cached individually?
We cache the entire schema.
Okay.
But that is a thought that we had, was to sort of break it down into specific maybe categories of types, because when you're changing something, you're maybe only changing one type. But that was a bit out of scope for when we were tackling the project.
Okay.
Yeah.
Thank you.
Yes. Let me pass the microphone over.
Hello. Yeah.
Hello.
So you said all the customer graphs are connected, right? So do you share the same namespace for all the types?
Yeah, so that's actually a great question. The customer graphs are connected within each customer. And in the Benchling data model, a customer can create organizations for their types. So we're actually namespacing by organization for each customer.
Okay.
Yeah.
So also another question is that, remember the last slide you're talking about the request, you generate just a part of the graph. So do you mean for each request you generate the graph, or you cache the graph?
Yeah, we are generating a subgraph on every request.
So each query you generate a subgraph?
Yep, and that's because the graph has to be fresh for every request. Like, imagine someone sends a request, changes a type, maybe loses permission for a type. It would sort of be a data integrity issue if we show them data they couldn't see.
Okay, I see.
Yeah.
Okay, thank you.
Yeah. Oh, question back there.
Sorry, thanks. Hey, so are you guys working on SDKs for the types? And if so, like, how do you handle the dynamic types in that case?
Yeah, we do not have an SDK for our GraphQL API at the moment. But I imagine that is also going to be in the future kind of an issue with all the dynamic types. Oh, up here.
Have you considered having like a centralized schema that has all the types and then just like a filtering out the graph at the runtime, and like so when they introspect like based on like rules or like policies, just filter out the like those pieces from the schema?
Do you mean like a centralized schema per customer or
No,
for everybody?
for everyone.
Oh, yes. That would be really tricky. I think we would probably end up with like hundreds of thousands of types in that case. And so that would likely be pretty bad for infrastructure for generating it and sort of things like that. We did, though, think for each particular customer. So each user has a view of their graph for a particular customer. And so that is something we do. We kind of do a user's view of the graph for a customer. Yeah. Cool. Any other questions? Great. Well, in that case, we can wrap up a couple of minutes early. Thanks, everyone, for coming.